We are going to start module 1 of chapter 10. In this module, we shall discuss some applications of classical mechanics in theory of relativity. The development of classical mechanics is based on some definitions and postulates. These postulates are valid if the velocity involved there is much less than the velocity of light. But these postulates cannot represent the classical facts if the velocity involved there approach the speed of light. In such cases, we need a general theory. Let us search for a theory. In this module, we shall discuss the necessity of theory of relativity, then Galilean transformation will be obtained, its drawback will be discussed, then we shall discuss about the principle of relativity and obtain the special Lorentz transformation formulae. Let us discuss about the Galilean transformation. From the figure, that is figure 10.1, you can find that there are two frames or systems. One is S system, another is S dash system. O is the origin of S system, whereas O dash is the origin of S dash system. P is the position of the particle, its position vector is r vector with respect to the origin O, that is with respect to the fixed frame S, whereas its radius vector is r dash vector with respect to the origin O dash. S is an inertial frame. Since at the initial time both the systems are at the same position, so both origins O and O dash were coinciding. After time t, the S dash frame shifted to the present position. As S dash frame is moving with uniform velocity capital V vector with respect to S frame. So, O into O dash is given by V vector into time t. From vector triangle law, one can easily find that r vector is equal to r vector dash plus capital V vector into t. If we shift V vector t on the left hand side, then we can get r vector dash is equal to r vector minus V vector into t, t being the time. Writing in component form, we get x dash equal to x minus capital V suffix x into t, y dash equal to y minus capital V suffix y into t, z dash equal to z minus capital V suffix z into t. X dash, y dash, z dash are the components of r dash vector, while x, y, z are the components of r vector. Capital Vx is the component of V vector along x axis. Capital V suffix y is the component of velocity vector capital V with respect to y axis. Capital V suffix z is the component of velocity vector along z axis. If we differentiate the relation given by 10.1 with respect to time t, we get r dash vector dot equal to r vector dot minus capital V vector. Here dot means the time derivative taking ordinarily. In component form, equation 10.2 gives x dot dash equal to x dot minus capital V suffix x, y dot dash equal to y dot minus capital V suffix y, z dot dash equal to z dot minus capital V suffix z. The transformations given by 10.1 and 10.2 are called the Galilean transformations. Equation 10.1 is the Galilean transformation for coordinate, since it connects the coordinates of two frame S and S dash, whereas 10.2 gives the Galilean transformation for velocity, since these are the relation between the velocities of two frames, that is S and S dash. If we again differentiate 10.2 with respect to time t, then we have r dash vector double dot equal to r vector double dot. That means acceleration in both frames are equal. If we denote r vector double dot equal to f vector and r vector double dot dash equal to small f vector dash, then we get small f vector equal to f vector dash. Thus, the accelerations of p are same in both the systems. So, if Newton's second law of motion, capital F vector equal to mass into acceleration, that is applied force capital F vector is equal to mass into acquired acceleration small f vector, holds in one system, then it should hold in the other system. So, one can conclude that a system moving uniformly with respect to an inertial frame is again an inertial frame. Now, let us discuss about the drawback of Galilean transformation. We have already obtained the Galilean transformation. Let there be a source of light at the origin of the system capital S, emitting spherical waves travelling with the speed of light c. Let r vector be the radius vector of a point on some given wave surface. Then in frame capital S, the velocity of the point on the wave surface is given by r vector dot equal to small c into n vector. Please note that r vector dot on the left hand side is the velocity vector, c is the speed of light. So, to making it vector, we have multiplied the unit vector n with c. N is the unit vector along r vector. So, both left hand side and right hand side are consistent. According to equation 10.2, the corresponding wave velocity in the system capital S dash moving with uniform velocity capital V vector with respect to capital S is given by r dash vector dot equal to small c into n vector minus capital V vector. One can get this result from the figure by using the vector triangle law or with the help of Galilean transformation. From this, it is very clear that for the system capital S dash moving with uniform velocity capital V vector with respect to the source of light, the magnitude of the wave velocity in general will no longer be small c, which is nothing but the speed of light. Moreover, as the radius of the wave surface depends on the direction, the waves will no longer be spherical, but a long series of experiments, especially the famous experiments of Michelson and Morley, have shown that the velocity of light is always the same in all directions and is independent of the relative motion of the observer, the transmitting medium and the source. Thus, the Galilean transformation cannot be correct and must be replaced by other, the Lorentz transformation, which will preserve the velocity of light in all the systems. Later on, Einstein showed that such a transformation requires revision of the usual concepts of time and simultaneity. From the experimental fact, he proceeded further that the speed of light is constant in all systems. As a basic postulate, he generalized that all phenomena of physics appear the same in all uniformly moving systems. In this module, we have already shown that Galilean transformation cannot provide accurate result at high speed. So, we have to replace the Galilean transformation by some other transformation. Such transformation must be linear, and in this transformation at the limit of low speed we can get the result for non-relativistic case. Moreover, under this transformation the speed of light should be uniform in each and every inertial frame. In this module, we shall obtain such transformation, popularly known as Lorentz transformation. Now, let us discuss principle of relativity. In physics, the principle of relativity is the requirement that the equations describing the laws of physics have the same form in all admissible reference frames. In 1905, Einstein proposed that the laws of physics are the same in every inertial frame, that is, there is no preferred inertial frame. This is known as Einstein's principle of relativity. Let us discuss about the Lorentz transformation. To establish Lorentz transformation, two important postulates are required. Number 1, principle of constancy of the velocity of light. The velocity of light or the velocity of propagation of electromagnetic disturbance in free space is universal constant small c, which is independent of the reference frame. Next, equivalence postulate. When properly formulated, the laws of physics are invariant to a transformation from one reference system to another moving with uniform, that is linear, relative velocity. Let us go through the figure 10.2. Here two systems have been considered, S and S dash. The origin of S system is O, whereas origin of S dash system is O dash. The x and x dash axis of S and S dash systems coincide, whereas y and y dash axis are parallel. Similarly, z and z dash axis are parallel. S dash frame is moving with uniform velocity small v with respect to fixed frame capital S. Capital P is the position of the particle whose coordinates are given by x, y and z. Here special type of coordinate system have been chosen, please note it. Both the frames S and S dash are inertial. Let the frame S dash is moving with respect to capital S with a constant linear velocity in the direction of common x axis. Y and z axis are parallel, that is, the Cartesian axis of capital S and S dash are parallel to each other, and that S dash is moving relative to S with a velocity small v in the positive direction. Let us consider an event which occurs at a point P x y z in frame capital S at time t. Then x, y, z and t are the space time coordinates of the event in capital S. Since x, y, z are the space coordinates, whereas t is the time coordinate. X, y, z are measured by a standard measuring stick which is at rest in frame capital S and at time t. The time t is read on a standard clock kept at rest in frame S at the point P. In the system capital S dash, an event is also characterized by the space time coordinates x dash, y dash, z dash, t dash. The coordinates x dash, y dash, z dash and time t dash are found by the same way as the coordinates in S with the help of a measuring stick, standard clock which is at rest in capital S dash. Our aim is to find the transformation between the space time coordinates of the same event in capital S and capital S dash systems. It is easy to note that any uniform translatory motion relative to capital S is also uniform relative to capital S dash. So, the variables x dash, y dash, z dash, t dash must be linear functions of x, y, z, t. Let us assume that the origins of the two systems capital S and capital S dash coincide at t equal to t dash equal to 0. Now, let us consider all those points in frame capital S dash which form a plane y dash equal to constant. If we take the constant as a dash and considering the plane parallel to x dash z dash plane, these points will also form a plane small y equal to small a which is again constant in capital S parallel to xz plane. The distances small a and small a dash are measured with the help of measuring sticks which are at different states of motion, and therefore, the ratio small k equal to a dash divided by a must depend on velocity small v. Since S dash frame is moving with respect to the fixed frame S with a velocity small v which is uniform. So, a dash divided by a is equal to k dependent on small v. If we interchange the roles of frames S and S dash, that is, if S is moving with respect to S dash with uniform velocity small v in the direction of positive x dash axis, then we get a divided by a dash equal to k function of v, that is reverse of above result. Multiplying these two results, this one and this one, we get k square equal to 1. So, k equal to plus minus 1. Let us interchange the roles of capital S and capital S dash. That is, if we consider capital S is now moving with respect to frame capital S dash with uniform velocity small v in the direction of positive x dash axis, then we have small a divided by a dash equal to small k function of v, that is the reverse of this result. Left hand side has been reversed. Multiplying these two, we get k square equal to 1. Taking square root, we get k equal to plus minus 1. Since positive direction of y and y dash are same, please recall the figure. You can find that y and y dash of positive direction are same. So, we can take k equal to 1, hence we have y equal to y dash. Similarly, one can easily prove that z equal to z dash. Let us consider that light signal in frame S and in frame S dash is propagated in the directions with the same velocity c. It is propagated in all directions with the same velocity c. In S, the spherical light wave is given by x square plus y square plus z square equal to c square into t square. X, y, z are the space coordinates, while t is the time. If we look into this, then this gives the square of the dimension of length. So, the right hand side will be consistent with the left hand side. C gives the speed of light, this is the time. The product of C into T gives the dimension of length and its square. So, both left hand side and right hand side are dimensionally consistent. In the same manner, in frame S dash, the light wave is given by x dash square plus y dash square plus z dash square equal to c square into t dash square. X dash, y dash, z dash are the space coordinates in frame S dash, while t dash gives the time in frame S dash. C, as usual, is the speed of light. We can write this in this way. Similarly, this can be written as this, that is s dash square equal to x dash square plus y dash square plus z dash square minus c square into t dash square. Please note that the frame S is fixed, while the frame S dash is moving with uniform velocity v in the common direction of x and x dash axis. So, x, y, z, t and x dash, y dash, z dash, t dash have a linear relationship. Thus, we can write s dash square is proportional to s square. That is, s dash square equal to k function of v into s square. K is the constant of proportionality which depends on velocity v, as we already mentioned that S dash frame is moving with respect to fixed frame S with uniform velocity v. Arguing as above, we can easily prove that k is equal to 1. So, this gives s dash square equal to s square. Thus, one can say that the quantity x square plus y square plus z square minus c square into t square remains constant. That is, we have x square plus y square plus z square minus c square into t square equal to x dash square plus y dash square plus z dash square minus c square into t dash square. We have already proved that y dash equal to y and z dash equal to z. Substituting these two, we get this relation, that is x dash square minus c square t dash square equal to x square minus c square into t square. X dash and t dash have linear relationship with x and t. Let x dash equal to alpha into x plus beta into t, while t dash equal to gamma into x plus delta into t. Alpha, beta, gamma, delta all are unknown. We have to find its values. Let us consider the motion of the point O dash, that is motion of the origin of the frame S dash. At O dash, x dash is equal to 0. Substituting this, we get alpha into x plus beta into t equal to 0. From this, we can calculate x divided by t, which is given by minus beta divided by alpha. Please note that left hand side, that is x divided by t, gives the velocity with which the frame S dash is moving with respect to frame S. So, this is v, that is it is the relative velocity. If we consider the motion of the point O, O is the origin of the frame S, then we have x equal to 0. Substituting x equal to 0, we get x dash equal to beta into t and t dash equal to delta into t. If we calculate the ratio x dash divided by t dash, then we get this is the velocity of frame S with respect to frame S dash. This gives minus v, because if frame S dash moves with respect to frame S with a velocity v, then frame S moves with a velocity minus v with respect to S dash. Therefore, we have x dash divided by t dash equal to beta divided by delta equal to minus v. From this and this, we get beta divided by alpha equal to beta divided by delta, which implies alpha equal to delta. If we substitute this in the expression of x dash and t dash, we get x dash equal to alpha into x minus v into alpha into t. This can be written like this one, and t dash is equal to gamma into x plus alpha into t as alpha equal to delta. We have substituted this value. Now, putting those values in this equation, we get x square minus c square into t square equal to alpha square into x minus v into t its whole square minus c square into gamma into x plus alpha into t its whole square. We have just substituted the value of x dash and t dash and get the next line. This is of the form a minus b whole square, this is of the form a plus b whole square. This can be written like this one. Here we have taken the coefficients of x square here and coefficients of the product term x into t here and the coefficient of t square here. Comparing the coefficients of x square, we get alpha square minus c square into gamma square equal to 1. Comparing the coefficient of product term, we get alpha square into v plus c square into gamma into alpha equal to 0, since on the left hand side there is no product term of x and t. Comparing the coefficient of t square, we get alpha square into v square minus c square equal to minus c square. We get this equation. Solving these, we get alpha square equal to this, which can be written like this one. Thus, we get alpha equal to 1 divided by square root of 1 minus v square divided by c square. In a similar fashion, solving for gamma, we get gamma is equal to minus v by c square into alpha. Substituting the value of alpha already obtained, we get this one. This can be written in this manner. Now, the Lorentz transformation formula becomes x dash equal to x minus vt divided by square root of 1 minus v square by c square, y dash equal to y, z dash equal to z, and t dash equal to t minus v divided by c square into x divided by square root of 1 minus v square by c square. This is known as direct Lorentz transformation formula. One can obtain the inverse Lorentz transformation formula in this form, just replacing x by x dash, y by y dash, z by z dash, t by t dash, and vice versa, and also replacing v by minus v, we have obtained the inverse Lorentz transformation formula. Remarks. Let us consider the case when v much less than c. In that case, v by c tends to 0. If we substitute this direct Lorentz transformation formula already obtained, we get x dash equal to x minus v into t, y dash equal to y, z dash equal to z, t dash equal to t. We have obtained this result from here, just substituting v by c tends to 0 here and here, we get this result. The Lorentz transformation formula 1 is called special Lorentz transformation because here we have used special type of coordinate axis, where in two frames have the same x and x dash axis, that is x axis of frame S and x dash axis of frame S dash are coinciding, while y and y dash axis are parallel to each other. Similarly, z and z dash axis are parallel to each other. That is why we have used the word special. In 1905, Einstein proposed some postulates. These postulates and their consequences develop the special theory of relativity. In this module, we have discussed about this and also obtained the Lorentz transformation formulae. This gives the formula for time also. This is the basic difference with the Galilean transformation. In Galilean transformation, we have only the transformation formulae for space coordinate. In this module, we have discussed the detail about it.